Hello everyone, myself Santanu Kundu. I welcome you all to this lecture of soft computing techniques. This is the third lecture of module 12. So in this module, we have studied introduction to artificial neural networks. We solve one questions by using back propagation algorithm. In this class, we'll try to understand the some concept of intelligent techniques, hybrid techniques, and Neuro-Fuzzy system. First is that intelligent techniques. Intelligent techniques refers to methodologies or algorithms that enable machines to exhibit behaviors that can be perceived as intelligent. These techniques are central to the fields of artificial intelligence, machine learning, and related areas. They are designed to solve problems that require human-like reasoning, learning from data, making decisions, and dealing with uncertainty or imprecision. First one is that neural networks. Neural networks are a set of algorithms inspired by the way biological neural networks in the human brain process information. They are made up of layers and interconnected nodes or neurons which can be trained to recognize patterns, classify data, and make predictions. Applications. Neural networks are widely used in image and speech recognition, predictive analytics, natural language processing, autonomous vehicles, and other applications that involve learning complex patterns from data. Strengths. Ability to model complex nonlinear relationships, automated learning from data without needing explicit programming of rules. Limitations. Lack of interpretability or difficulty in understanding, that is the black box problem. Require large amounts of data for effective training, computationally expensive. Next is that fuzzy logic systems. Fuzzy logic systems deal with reasoning that is approximate rather than fixed and exact. Unlike traditional Boolean logic, which operates with binary true-false values, fuzzy logic allows for reasoning with degrees of truth or certainty, which is especially useful for handling uncertainty and imprecision in decision-making processes. Applications commonly used in control systems, as for example, washing machines, air conditioners, robotics, decision support systems, and expert systems where information is uncertain or incomplete. Strengths, ability to handle imprecision and vagueness in data, decision making based on human like reasoning. Limitations, manual knowledge acquisition is time consuming. The rule base can grow quickly as the number of variables increases, leading to complexity. Next one is genetic algorithms. So genetic algorithms are optimization technique inspired by the process of natural selections. They use mechanisms such as selection, crossover, and mutation to evolve solutions to problems over successive generations. Used in optimization problems, machine learning, engineering design, robotics, and artificial life simulations. Strengths, effective for solving optimization problems with large complex search spaces, can handle nonlinear and non-differentiable functions. Limitations, requires many iterations which can be computationally intensive. Finding the best solutions can be slow. Next one is the expert system. Expert systems are AI systems that emulate the decision-making abilities of a human expert in specific domain. They rely on a knowledge base that contains expert knowledge and a set of inference rules to make decisions or solve problems. Applications common in medical diagnosis, financial decision making, customer support, and troubleshooting systems. Strengths, provide consistent decision making based on expert knowledge, can operate in specialized domain specific areas. Limitations, knowledge acquisition is difficult and requires human expertise. They can be inflexible and cannot adapt to new information easily. So there is a comparison between expert system, fuzzy systems, neural networks, genetic algorithms. So we compare with the parameter. knowledge representations, uncertainty tolerance, imprecision tolerance, adaptability, learning ability, expansion ability, knowledge discovery, and data mining, maintainability. So this line means bad. Single arrow means it is rather bad, it's not so bad. Double arrow means it is rather good, means average, and three arrow means uh, three tick marks means good, or it can consider as very good. So knowledge representations in expert systems, it is average. In fuzzy system, it is very good. Neural network is bad, and genetic algorithm, it is rather bad. Similarly, for uncertainty tolerance in expert system, this means this is average. This means very good, also very good. Imprecision tolerance expert system is bad. It is very good, and also very good, and also very good. You can consider as good. Adaptability here in expert system is bad. Here it's not so bad. Here you can say good or very good. I mean good, good. Learning ability is bad. Here bad. Here good. Here good. Expansion ability good, good. This is bad, not so bad. Knowledge discovery and data mining. Here it is bad. Here it is not so bad. This is good. This is it's you can say is rather good or average. Similarly, maintainability in expert system, it is bad. Here it is the not it is can say it is average or rather good. It is good and also rather good. So these are the comparison between expert system, fuzzy systems, neural network, and genetic algorithms. Now we'll try to learn few more intelligent techniques. So few more intelligent techniques. First one is or the, you can say the fifth one is support vector machines, SVM. Support vector machines are supervised learning model used for classifications and regression tasks. They work by finding a hyperplane that best divides a dataset into different classes. SVMs are widely used in image classifications, bioinformatics, text categorization, and face recognition. Strengths effective in high dimensional spaces, can model nonlinear decision boundaries using kernel tricks. Limitations computationally expensive for large datasets, can be sensitive to noise and outliers. Next one is that reinforcement learning. Reinforcement learning is a type of machine learning where an agent learns how to behave in an environment by performing actions and receiving rewards or penalties in return. The goal is to maximize cumulative rewards over time. Then RL, that is reinforcement learning, is commonly used in robotics, game planning, autonomous vehicles, and optimization problems. Strengths can learn complex behaviors through trial and error, while suited for dynamic real-time decision-making environments. Limitations requires a lot of computational resources and time to train, can be hard to implement for problems with long-term planning. Next one is that Bayesian networks. Bayesian networks are graphical models that represent a set of variables and their probabilistic relationships. They are based on Bayes theorems and are used to model uncertainty in complex systems. Used in diagnostic systems, predictive analytics, medical decision making, and risk analysis. Strengths, well suited for representing uncertainty and probabilistic relationships, can handle incomplete data and make predictions even with missing informations. Limitations can be computationally expensive for large scale networks, requires expert knowledge to define probabilistic relationship between variables. Next one is that swarm intelligence. Swarm intelligence is inspired by the collective behavior of decentralized systems such as behavior of birds flocking or ant colony. Techniques like ant colony optimizations and particle swarm optimization are a part of swarm intelligence. Application used in optimization problem, network routing, robotic swarm behavior, and multi-agent systems. Strengths can find optimal or near optimal solutions in complex search spaces, robust and flexible in dynamic environments. Limitations may require many iterations to converge to a good solutions. Lack of guarantees for finding the global optimal solutions. Next one is natural language processing. Natural language processing is a field of AI that focuses on the interaction between computers and human language. NLP enables machines to read, interpret, and generate human language. Application used in chatbot, speech recognition, sentiment analysis, language translations, and information retrieval. Strengths allows machines to process and understand human language, facilitates human computer interaction and communications. Limitation language is complex and often ambiguous, making NLP tasks challenging. Require large datasets for training language and model effectively. Next one is deep learning. Deep learning is a subset of machine learning that uses neural networks with many layers, hence the term deep, to model complex patterns in data. It's particularly powerful in tasks like image and speech recognition. Deep learning used in computer vision, natural language processing, speech recognition, autonomous systems, and AI-powered applications. Strengths excellent at handling large-scale unstructured data like images, audio, and video. Can automatically learn features from raw data without manual feature extractions. Limitations requires large amounts of labeled data to train effectively. Computationally expensive require powerful hardware like GPUs. So intelligent techniques are backbone of many AI systems, each with its strength and weakness. Their choice depends on the nature of problem at hand, whether it's dealing with uncertainty, making predictions, interpreting data, or optimizing solutions. With the growing demand for smart systems across industries like healthcare, finance, robotics, and transportation, the development and integration of these intelligent techniques are becoming more crucial for achieving advancement in AI and solving complex real-world challenges. Intelligent techniques are their computational properties. Every intelligent technique in the field of artificial intelligence exhibits unique computational properties that make them particularly well suited for specific problems while rendering them less effective in others. These properties primarily include the ability to learn from data, the transparency in decision making, adaptability, and the ability to handle uncertainty. Understanding these properties helps in selecting the appropriate technique for different types of problems. For example, some techniques are designed to handle precise data while others are better at managing imprecision or uncertainty. Neural networks strengths. Neural networks are designed to recognize complex patterns and relationships in large datasets. They are widely used in tasks that involve classification, regression, and feature extractions, including image and speech recognition, recommendation systems, and predictive analytics. The networks learn from labeled data and adjust their weights to minimize prediction errors. This makes them ideal for problems where large volumes of data are available and the patterns within the data need to be learned. Limitations. Despite their ability to make accurate prediction, neural networks often lack explainability. The decision-making process within neural networks is not clear, making it difficult to understand how a particular output was derived. This characteristic is problematic in domains where transparency is crucial, such as healthcare, finance, and legal fields, where stakeholders need clear justification for automated decisions. Next one, fuzzy logic system. Fuzzy logic systems are particularly effective in dealing with uncertainty and imprecision, especially in situations where the available information is vague or unambiguous. These systems are linguistic variables such as high, medium, and low, and fuzzy then rules to model human reasoning. They are extensively used in control systems such as temperature regulation, automatic gear shifting in vehicles, and robotic control systems. The key advantage of fuzzy system is their interpretability. Decision making in this system is based on rules that are easily understood by humans. Limitation. One of the major challenges with fuzzy logic system is the difficulty of knowledge acquisitions. The creation of rules, especially in complex domains, require expert input and is often a manual, tedious, and error-prone process. Moreover, the system's ability to handle a large number of input variables reduce says because the rule base can grow exponentially with the number of variables. Application domains for hybrid systems. Hybrid systems have found successful applications in wide range of fields due to their ability to address complex and multifaceted problems. Many real-world problems contain sub-problems that require different computational approaches. By using hybrid systems, these distinct sub-problems can be tackled by appropriate techniques, resulting in improved efficiency, and performance. Example of hybrid system applications. First one is process control. Hybrid systems can optimize industrial processes by using fuzzy logic to control variables like temperature, pressure, and flow, while neural networks predict future trends or detect anomalies in the system. Engineering design. The design tracks neural networks can be used for optimization. The fuzzy system can handle subjective decision makings or imprecision in requirements. Financial trading. Neural networks can analyze historical market data and detect patterns, while fuzzy systems help in making trading decisions based on uncertain or incomplete market information. Credit evaluation. Hybrid systems can be used to analyze customer data using neural networks or pattern recognition and fuzzy logic for assessing risk based on subjective criteria such as customer behavior. Medical diagnosis. In healthcare, hybrid system may combine neural networks to identify patterns in diagnostic data, as for example, medical scans or genetic information, with fuzzy systems to infer diagnosis based on expert knowledge. Cognitive simulations. These systems are increasingly used in simulating human cognitive processes, where neural networks model learning and decision making, and fuzzy systems provide reasoning that mirrors human ambiguity and imprecision. Neural network fuzzy systems and hybrid approaches. Integration of neural network with fuzzy logic, that is Neuro-Fuzzy. One of the most powerful approaches in hybrid intelligence systems is the integration of neural networks with fuzzy logic. Neural networks are often used to optimize the membership functions of fuzzy systems, thereby improving their decision-making abilities. In practical application, fuzzy logic is used to process imprecise information, while neural networks tune parameters, adjust rules, and enhance performance by learning from data. This synergy has proven beneficial in areas like automatic control system and decision support systems. Manual tuning in fuzzy systems. The traditional fuzzy logic systems, the membership function need to be designed and tuned manually, which can be highly complex and labor-intensive tasks. Experts in the field must determine the fuzzy sets and define appropriate rules. In complex applications, this tuning process can take a significant amount of time, making the system inefficient for real-time applications. Neural networks automating fuzzy systems. To overcome these challenges, neural network techniques can be used to automatically adjust the membership functions of fuzzy systems. This automation is not only reduces the time and cost development but also enhances the adaptability of the fuzzy systems. Neural networks can fine tune with parameters in real time, allowing the system to evolve and improve as more data becomes available. Extending neural networks for fuzzy systems. To address the limitation of knowledge acquisition in fuzzy systems, researchers have developed methods to extend neural networks in ways that allow them to automatically extract fuzzy rules from numerical data. This hybrid approach leverages the learning capabilities of neural network while maintaining the interpretability of fuzzy systems, making it a powerful tool for complex decision-making tasks. Cooperative approaches. Optimizing fuzzy systems. In cooperative approaches, neural networks can be used to optimize the membership functions of fuzzy system by adjusting parameters that influence decision making. This enables the fuzzy system to perform better over time and adapt to new data. Pre-processing and rule extractions. Another key aspect of cooperative approaches is using neural networks to pre-process data before it is fed into the fuzzy systems. By analyzing patterns and extracting relevant features from raw data, neural networks can assist in creating fuzzy rules or improve the rule extraction process itself, reducing the reliance on human expertise. Future of hybrid system. The development and use of hybrid systems that combine the strength of neural networks and fuzzy logic are rapidly increasing, particularly in complex application areas where the both pattern recognition and decision making under uncertainty are required. This hybrid system promise to improve industries like healthcare, finance, and robotics by providing more efficient and interpretable and adaptable solutions. As the research progresses, we can expect to see even more sophisticated hybrid systems that push the boundaries of AI and solve increasingly complex problems. So Neuro-Fuzzy. So first was the standard neural network. So you have studied that these are neurons. So these are the weight the input. So output is the activation function of W1 into x1 plus W2 into x2. So this F sigmoid function may be any activation function. If we employ other operation like T norm means the minimum, T norm AB means minimum of AB, T co-norm means maximum of AB. To combine the incoming data to neuron, we, we obtain what we call hybrid neural networks. So if we get simple activation function, then we can get simple network. If we use the fuzzy logic, we'll get the hybrid neural network. This modification lead to a fuzzy neural architecture based on fuzzy arithmetic operations. Let us express the inputs, which are usually membership degrees of fuzzy concept x1, x2 and weights w1, w2 over unit interval 0, 1. A hybrid neural network may not use multiplication, addition or sigmoidal functions because the result of these operations are not necessarily are in the unit interval. So definition 1, a hybrid neural network is a neural network with creep signals and weights and creeps transfer functions. However, we can combine xi and wi using t norm, t conorm or some other continuous operations. We can aggregate P1 and P2 with T norm, T conorm or any other continuous functions. It can be any continuous function from input to output. We emphasize here all inputs, outputs and the weights of hybrid neural network are real numbers taken from unit interval 0 to 1. A processing element of a hybrid neural network is called fuzzy neuron. So we have right here n fuzzy neuron. So first one we signal xi and w are combined with a conorm s, I mean maximum of these two. The input information of pi aggregate by triangular norm t to produce the output like and p1 and p2. So it is the t norm. So first to find the maximum of these two, then until the minimum of this. So of the neuron. So here is the first you find maximum, then you find minimum. So x1. So first to find the maximum of these two, then you ultimately find the minimum of these two. So that is AND fuzzy neuron. Similarly, there is a OR fuzzy neuron. So first you find the here it is OR. So find maximum. So first find minimum of these two. So T norm of these two, then find the maximum of these two. So this is known as the OR fuzzy neuron. So this is one system of fuzzy neuro-fuzzy systems. So here there are 5 layers: layer 1, layer 2, layer 3, layer 4, layer 5. So this is the input layer. So you know that is fuzzy set. So x1 is, so you get a mu x1. So layer 3 is, in layer 3 you will find roots. Layer 4 you combine the roots like that, and then ultimately this is the defuzzification. So see the rules of each layer. So each layer in the Neuro-Fuzzy system is associated with a particular step in fuzzy inference process. Layer 1 is the input layer. Each neuron in this layer transmits external creep signals directly to the next layer, that is yi equal to xi1. Layer 2 is the fuzzification layer. Neurons in this layer represent fuzzy sets used in the antecedents of fuzzy rules. A fuzzification neuron receives a creeps input and determines the degree to which this input belongs to the neuron fuzzy sets. So that is the layer 2. In layer 3 is the fuzzy rule layer. Each neuron in this layer corresponds to a single fuzzy rule. A fuzzy rule neuron receives input from the fuzzification neurons that represent fuzzy sets in the rule antecedents. For instance, neuron R1, which corresponds to the rule 1, receive input from A1 and B1. So check it. These rules R1 received from A1 and B1. So that is layer 3. In layer 4 is the output membership layer. Neurons in this layer represent fuzzy sets used in the consequent of a fuzzy rules. An output membership neurons combines all its input by using the fuzzy operations union. These operations can be implemented by the probabilistic OR, that is this X1 or like that. So the value of mu1 represents the integrated firing strength of fuzzy neurons R3 and R6. The next layer, that is layer 5, is the defuzzification layer. Each neuron in this layer represents a single output to the neuro-fuzzy systems. It takes The output fuzzy sets clipped by the respective integrated firing strength and combine them into a single fuzzy set. Neuro-fuzzy system can apply standard defuzzification methods, include the centroid techniques. We'll use the sum product composition method. So sum product composition calculates the creep's output as the weighted average of the centroid all output membership functions. For example, the weighted average of the centroid of clipped fuzzy set C1 and C2 is calculated as y equal to mu C1 into A C1 into B C1, like mu C2 into A C2 into B C2 divided by mu C1 into B C1 plus mu C2 into B C2. So we'll solve some numerical questions. So in conclusions, today we understood different intelligence systems, concept hybrid systems, neuro-fuzzy systems. So question is that write the uses of intelligent systems. So this is the reference of today's class. Thank you.